Good morning, students. Today we will discuss about Poissons and Laplace equations. Students, this topic is very important from examination point of view since around 10 marks question compulsorily comes from this particular topic. So it's my kind request to please go through the examples, explanations, and then try to solve it properly. If there is any problem, then you can contact me anytime. This equation title is Laplace and Poisson's equation. Now, first of all, let me tell why these equations are important. Now, every time when we are going to find the electric field, line charge, or through a surface charge, or through a sheet charge, E is uniformly distributed over the surface. Or we can find electric potential by using the formula E is equal to minus of del V when shape of the surface is known. But there are certain cases where the charge distribution is not uniform throughout the surface, but resides on the boundary of the system. So in this case, neither we know the potential about the particular charge or nor the volume. So nor the potential difference. So in that case, the use of Poisson's equation comes into picture, where the charges rise along the boundary of the system. Moreover, this equation can also use to find the boundary conditions, which you will study later on. Now, Laplace equation is one of the case of Poisson's equation. These Laplace and Poisson's equations are very important as numerical point of view. Now, this is the derivation which always comes in the exam. For linear material, Poisson's and Laplace equation are derived basically from the Gauss law. As already we know that del dot D is equals to Q, that is the charge, that is the Gauss law equation. And we can also say that del dot D is equal to rho V, which is the point form of Gauss law. Taking this point into consideration, we will find the equation based on Gauss law. Replace this D by epsilon E. As we all know that D is nothing but it is epsilon E. So we can write it here, D into epsilon E is equal to rho V. This epsilon is a constant. We can take it as out. We can write it as del dot E is equal to rho V upon epsilon. Now we all know that E is electric. We can also write it as minus of del V, gradient of potential. So we can write here del dot minus of del V is equals to rho V upon epsilon. We can also write del dot del V, taking minus sign this side, minus rho V upon epsilon. So this thing is clear to you. Del dot del V is minus of rho V upon epsilon. Now we can also write it as del square V is equal to minus rho V upon epsilon. Now friends, this particular equation, del square V is equal to minus rho V upon epsilon, is known as Poisson's equation, and which states that the potential distribution in a region depend upon local charge distribution. Now in many problems, in many boundary problems, charge distribution is involved on the surface of the conductor, for which the free volume charge density is 0. Now what we can say that this rho V is equal to 0. In that particular case, del square V is equal to 0, and that particular equation is known as Laplace equation. So from the Poisson's equations, we can calculate Laplace equations. This is a particular case of Laplace equation, and this derivation is very important. It always comes in examination along with numerical. So we can say that del square V is equal to minus rho V upon epsilon is Poisson's equation, and del square V is equal to 0 is nothing Laplace equation. Now we'll see numerical one by one. Before doing numericals, we should know the formula. We should revise the formula of del V. So del V is del upon V del x of x, as I already told in the numerical. When this gradient work on a function, we convert it into a vector form. So del V is del V upon del x of ax plus del V upon del y of ay plus del V upon del z of az. So when it is a vector, it is del upon del x of ax plus del upon del y of ay plus del upon del z of del z. Now, when you have to do del square v is nothing but it is del dot v. So when you multiply it again by del, so we can say that del square v is equal to del square v upon del x square plus del square v upon del y square plus del square v upon del z square. Because when you multiply it, ax cancel. So it is del square v upon del x square, del square v upon del y square plus del square v upon del z square. Here x, y and z. So this is the formula of Poisson's equation or del square v in Cartesian coordinate. Remember this formula. Del square v in Cartesian coordinate system will become del square v upon del x square plus del square v upon del y square plus del square v upon del z square is equal to 0. Now in cylindrical coordinates, del dot v is del v upon del rho of a rho plus 1 by rho del v upon del phi of a phi plus del v upon del z of az. This we have already studied in del dot v of Cartesian system, and del dot a is 1 upon rho del by del phi of rho a rho plus 1 by rho del by del phi of a phi plus del by del z of del z. Again when you multiply it, this will become 1 by rho del by del rho of rho del v upon del rho plus 1 by rho square. When you multiply it, it will be 1 by rho square del square phi by del phi square of v plus del square v upon del z square is equal to 0. This is in cylindrical coordinates. You should remember this formula. For spherical, del dot v is del v upon del r of ar plus 1 by r del v upon del theta of a theta plus 1 by r sin theta del v upon del phi of a. So del dot a is 1 by r square del by del r of r square ar plus 1 by r sin theta del by del theta of a theta sin theta plus 1 by r sin theta del by del phi of a. Del square v is del dot del v. And this is the formula 1 by r square del by del r of r square del v upon del r plus 1 by r square sin theta del by del theta of sin theta del v upon del theta plus 1 by r square sin theta del v upon del phi of v. So you have to remember all these three formulas in Cartesian, cylindrical and spherical system. Now the application of Laplace and Poisson's equation. Using Laplace or Poisson's equation, you can obtain potential at any point between two surfaces when potential at two surfaces is given, or you can also obtain capacitance between these two surfaces. So when this question comes in examination, they always ask about the boundary condition. They always specify about the boundary condition, and they ask to find out the potential between the surface or the capacitance. So they will not specify by using Laplace and Poisson's equation. By own you have to learn, by own you have to think that this question is of Poisson's and Laplace equations. Since they have given boundary conditions and they are asking about the potential of the surface or the capacitance. So let us take an example. The example is like that. Two parallel conducting discs are separated by a distance of 5 mm at z is equal to 0 and z is equal to 5 mm. If v is equal to 0 at z is equal to 0 and v is equal to 100 at z is equal to 5 mm, find charge densities of the discs. Now here, since they have given this, that means it must be a problem of cylindrical system. If instead of this they have given plates, then it may be example of Cartesian system. But since they have mentioned here discs, so it will be a example of cylindrical system. And the boundary conditions are given. Z is equal to 0 and Z is equal to 5, V is equal to 0 and V is equal to 100. So by remembering this formula, you should understand that the formula for Poisson's equation. Now it is given that V is function of Z only. Now in Cartesian system again we are having x, y, z, and in cylindrical system we are having x, y, z. So it is a function of z only. So it is find that del square V is del square V upon del z square. There is no need to write about r coordinate and phi coordinate. Since in the last example, spherical coordinates, we can see the formula. Del square V is 1 upon rho of this plus 1 upon rho of this. This is a function of r and it is a function of phi. So there is no need to use this formula. Since only the z coordinate is given, so we can write del square V is equal to del square V upon del z square. Okay, now we have to find out V and Z. So integrating first one. When you integrate it, you will get dV by dz is equal to A. When you again integrate it, you will get V is equal to AZ plus B. You have to find out this condition. V is equal to AZ plus B. Now put all the values. Suppose when V is equal to 0 and Z is equal to 0. So here V is equal to 0 and Z is equal to 0. We will get the value of V is 0. So here I have put here and when V is equal to 0, Z is equal to 0. So put here 0 is equal to A into 0 plus B. So you will get V is equal to 0. V is equal to 100 and Z is equal to 5. V is equal to 100 and Z is equal to 5. Here Z is equal to 5 in this value. So A it is mm, so convert it into meters. It will be A into this plus B. So you will get B was 0. So you will get the value of A which comes out to be 20 into 10 to the power of 3. So this value in equation number 1. Put it here. So V is equal to AZ plus B. Our B was 0. So it is V is equal to 20 into 10 raised to the power of Z. Now this is the potential. Now in the question it is asked find the value of E. So E is equal to minus of del V. So it is del upon del rho of V A rho plus 1 by rho. This is the formula of V which I have already discussed. Del V upon del phi of A phi plus del V upon del Z of AZ. So E is del V upon del Z which is minus 20 of this. Once you know E, you can calculate D. D is epsilon 0 E. Okay. So this is D is epsilon 0 E. So you can calculate D. And rho s is the surface charge which is dn. It is plus or minus side on the surface. So it will be plus minus times of 0.177 into 10 raised to the power of minus 6 Z. So students, this we have done for cylindrical system. Kindly revise the formula and do the numerical. Thank you.